Hi, my name is Joe Kramer. I'm a high school physics teacher and a writer on OpenSciEd High School Physics 1. In this lesson, we actually build working generators that light up an LED. I'll go into detail about the specifications of the materials you'll need to get these generators working, because this moment is a truly beautiful one that your students will enjoy and remember if you can get it to work. And a lot of teachers have complained that the generators don't work. Certain choices that you make will make a huge difference. So I'll talk about that here. Students tend to be pretty skeptical that the generators will actually work. So when they see other groups get their generators working and then they finally get theirs working, there's this palpable excitement that spreads throughout the room. I want to make sure that you experience that in your class. First, some details about how we get here from lesson 4. In lesson 4, we discuss the concept of reliability, and we think more about which sources should be considered more reliable. But we realize that we don't have a clear picture of what makes these plants different from each other. So we're wondering what makes them different from each other? How do these plants actually work? An overview of the lesson at a glance. This is an investigation lesson that takes about 3 days. Preparing the generator materials and testing them and troubleshooting them can take some time the first time around. So plan on 60 to 90 minutes or more of materials preparation. I'll talk about this lesson in 4 main chunks over these 3 days. First, on day 1, we start by looking at a diagram of a wind turbine and a natural gas plant. We introduce some new conventions for energy transfer diagrams where we label the matter interaction on the arrows. We figure out that verbs can help us say a lot about what's going on in an energy transfer, but they can also point out when we do not understand what's going on. This specifically gets us to the idea of the generator. We can see that both types of power plants have generators in them. So we dissect a small generator, and this gives us a lot of questions about like what is actually going on inside this device. Can we make our own generator perhaps? So we collect these ideas on an exit ticket, and that takes us to day 2. We set out to build our own generator from the same basic parts that the dissecting generator had. We identify some criteria for success, and then we do successfully build our own generators. So we're wondering what other evidence we would need to figure out how this generator actually works. Um, we want to answer our own questions about these generators from evidence, so that takes us into day 3. We come back to class on day 3, and we use compasses to collect evidence about fields and changing fields. We discover it's really when the fields change that we transfer energy. So we model this out using the same matter interaction convention that we came up with for the power plants. But we still have questions about what's happening inside these wires because we can't really see what's going on in there. That's what takes us into lesson 6. So in summary, we figure out that the power plants spin a generator to produce electricity. The strength and position of the magnets, the number of wire wraps, the speed of spinning, all of these can affect the electrical energy output. And we see when we make our models that spinning a generator causes magnets to move, which changes fields, which transfer energy at a distance. Some key moments from these 3 days. First, when we develop these energy transfer diagrams initially, we use a convention of showing energy quantity in lesson 3. But in lesson 5, we switch that up. We introduce a new convention of labeling arrows with a single verb to indicate how matter interacts. For example, the wind pushes the blades, or the blades heat up the surroundings. This convention is the one that we use on the first major test or transfer task in lesson 6. So we want students to begin practicing it here. 2 big ideas. Question marks continue to be important, as you can see on this example model. for identifying places where we need to look deeper. And second, energy is always leaving the system to the surroundings on these diagrams. Whether or not we have a clear idea of where exactly this energy goes or how to label the arrow with a verb, we want students to identify it, even if the arrow has a question mark on it. The diagram of the natural gas plant is considerably more complicated than the wind plant. So it's set up where the class models the wind plant together, and then we use some of the things we've figured out to model the gas plant, either in partners or individually. Energy transfer diagrams can show a lot about what's going on when we label the arrow with a verb to show how matter is interacting. Uh, Next, one key piece of this modeling is identifying the places where we have questions so that we can answer those questions next. We can tell that the generator spins or moves, but we can't tell much more than that. And we definitely don't understand what's happening between the generator and the wires. So that's where we decide what to go, what to study next. Next, when this generator design challenge begins, the first design challenge is to try different arrangements of magnets. One key takeaway is that some arrangements do not cause a change in field as the nail spins. Similarly, a fast change will cause the LED to light, while a slow change will not. Later, when we build understanding about magnets and fields, we're using a compass as a tool to investigate these fields. One big takeaway about fields here comes from the idea that we can label this arrow that I've circled in red with the word change. There's a lot of complex physics tied up in this little arrow, but for many of us, this one word will be enough, at least for now. So we build this idea that matter changes and energy transfers often happen together, but they are different and we need to track them differently. Our generator model helps us see that we have a lot of questions about what happens inside the wire, both the coils of wire in the generator and the wires that we connect them to. So that takes us into our investigation of wires, which I'll talk more about in the next video. Some tips and tricks about how this energy and matter flow modeling works. First, in this natural gas diagram and the wind diagram, matter is color coded. So we can see by looking at colored arrows how matter flows through the system. And we can recognize that matter flow is different from energy transfer, but they are connected. So pay attention to the colors in these diagrams. Next, this is really important. The specifications matter a lot when we're building these generators. Small magnets will not produce a big enough change in field to light the LED. Everyone will be very sad and disappointed, including you. So invest in some big, strong magnets. At a minimum, I would use 3/8 inch diameter, 3/8 inch height cylindrical neodymium magnets. Next, the LED that we use is really important. The phrase ultra bright tends to mean that the LED puts out 5,000 MCD or more. Try to pay attention to this number and buy LEDs that have a high MCD number. Also, it helps to use red rather than green or white. I like to use really big nails. The size is 60D. They need to be ferrous so the magnet sticks to them, and they need to be between 4 and 6 inches long. You do want lots and lots of wraps of wire around these tubes. So 250 or a minimum 200 wraps of wire on each side, less than 5 centimeters apart from each other. If you wrap across the entire tube, you will not get wires that are close enough to the magnet. I like to have a very sensitive analog ammeter around to detect very small currents, because you can connect that to the wires rather than just connecting the LED, and you can see the needle move back and forth. Try to focus less on distinguishing electric versus magnetic fields, or field lines, or patterns or rules around field lines. Tip is especially important for seasoned physics folks. If you can find ways to do this stuff that feel coherent and valuable for your population, great. But the focus on this unit is more on just seeing the compass wiggle as evidence of changing fields. There's actually a lot of depth here. For example, the energy that makes the compasses move is energy that is not going to the wires. So it makes sense that the high output generator that you see on the right here barely makes the compasses wiggle at all, because so much of that energy is going to the wires instead. Try to encourage your students to think about this wiggling compass evidence with some real depth, and it'll pay off. Consider asking students to make their own version of this diagram, either at the beginning of lesson 6 or at the end of lesson 5. You can even add it to the engineering handout, so it sort of is a part of the engineering task. Something to give you a written record of students' own understanding of the generator. Lastly, some tips about how we manage terms and material on the wall. This idea of changing fields is really, really key. So we build that idea together. We do reference our previously created energy transfer diagrams, both on a poster and on these cards. And then we create our first diagram of the generator. This tends to be really key when we try to make diagrams of a motor on the lesson 6 transfer task. I'll see you again for lesson 6 when we use a simulation to investigate more about what's going on inside these wires.